Okay. So the last slide in part 2 says you need to be able to kind of differentiate between, you know, the I'm thinking of game. You guys said a characteristic of the cheeseburger. That's a property. And every property can kind of be divided up into, is that a chemical or physical property? You know, do we have to do some sort of chemical process to analyze it? And we'll talk more about chemical changes today. Okay, what is chemistry? You get new stuff. What is that? Okay. Or is it a physical property? So the color of sulfur is yellow. See, do you guys have the answers to these?
No, we have the right.
Okay, how many people, and I'll always go physical, chemical. How many people think that's a physical property? Me too. Okay, very good. And actually, I know the answers were shown before we started here. The next one, the fact that Fe iron can be transformed into iron oxide or rust. How many people think that's a physical change or property? How many think that's a chemical property? Me too. Very good. New substances, right?
I'm sorry, Mrs. Snipes.
That would have been the packet, the end of the last packet. Let's see. Part 2. It's a one-sheeter. It should be like I think a one-sheeter.
These are the
This one.
This one?
Okay, so this
Oh,
one.
right here. Okay, I'm sorry.
Thank you. Okay. Not everything can explode, right? People have respect for a stick of dynamite, you know. So the fact that dynamite can explode when you put a flame to that, how many people think that's a physical property? How many think that's a chemical property? Chemical. Yeah, chemical, exactly. It would be a great I'm thinking of question. Does your thing explode? All right. Now, density. Density basically is how kind of compact something is or how fluffy something is. We'll be talking more about density. But basically what you do is you set aside a chunk and you get a fix on its mass and its volume. And you go ahead and do a little division. So the fact that uranium is pretty darn dense, okay? How many people think that is a physical property? Okay, very good. You know, density would be a good thing to I'm thinking of, you know. Is it a very dense subject or is it a very low dense thing you're thinking of? Okay, low density. Okay, we talked about things changing phases, and we're going to talk a little bit more about that again today. So when you break chemical bonds of a solid, when you break intermolecular bonds of a solid, okay, when you break those things that are connecting the repeating units, those intermolecular bonds, your yellow ropes, okay, then something can melt. It'll go from a solid to a liquid. The fact that aluminum will melt at 933 Kelvin, how many people think that's physical? How many people think that's chemical? We'll be talking more about that. It is physical. The cool thing about that, no pun intended, is what I'm hoping, and some of this will help today when we talk about physical changes. It's a physical property because the aluminum that you started with as a solid, you jacked up the temperature. That's pretty warm, okay? And it went ahead and you broke those bonds between the aluminum particles. But if you were still to look at aluminum in its liquid state, it'd still be cute little aluminum atoms, okay? So no, in that case, atoms were changed in the process. Okay, so and melting point temperatures or melting temperature is always a physical property. Okay, the fact that, and this goes back to kind of the yellow, the fact that chlorophyll is green, how many people think that it is a physical property? Me too. Very good. Okay, so the next slide was the assignment slide. Okay, so now after the assignment slide, it should look something like this again. Maybe, maybe not. I kind of insert this picture a lot. Okay, good. Well, you recognize this is kind of the logic tree of matter. You know, matter can either be a pure substance or a mixture. And we talked about this in a previous part. And if it's a pure substance, your options are, basically, it's just the same atom, which makes it an element, a pile, you know, or a compound. There's two types of compounds. I kind of introduced you to that. If your substance is not pure, that means you have two or more pure substances that are tossed together, just like you toss a salad together. Okay, and kind of the examples here are, this looks like coffee with sugar, okay, and this actually is oil and water. So oil and water is heterogeneous. It's not the same throughout. This coffee and sugar and water is homogeneous. It is the same throughout. Okay. So even just this morning, we talked again about physical properties and chemical properties. So at the end of this part, one last thing I want to hit is when matter changes, makes physical changes, or when matter makes a chemical change. Chemical changes are more dramatic. But let's kind of focus on physical changes. Physical changes in matter go right along with your physical properties, kind of. What we've been talking about, physical properties. Okay, so a physical change is said to occur in a chunk of matter if you end up like with the aluminum. You've got the same atoms. Or like with water, if you take water and go from a solid to a liquid, you still have cute little water molecules. Okay, same stuff. No new substances are formed. Okay, so sometimes I would say no new substances. Formed. Same old, which can be a good thing. Okay, so examples of a physical change, of matter undergoing a physical change, is if you change its liquid, solid, gas. Okay, so it's still the same matter. You're just adding those bonds, adding those yellow bonds, or you're breaking those little yellow bonds. Okay, so phase changes are all physical changes. Another, it doesn't look like it maybe, but if you go ahead and put something in your blender, like if you put your pizza in the blender, okay, that actually is just a physical process. You feel like you're breaking it up, and literally you are breaking stuff, but you're not breaking chemical bonds. You're not breaking the tomato little molecule that makes it a tomato, or the bread molecule that makes it the bread molecule. You're breaking the intermolecular bonds. Kind of like pureeing it in the blender would be like a type of kind of like liquefaction, in that you're breaking those bonds mechanically instead of with energy. So physical changes. So a minute ago, or on that slide that had the coffee cup with the little cubes of sugar outside, okay, when you take your sugar and you dissolve it on your coffee like that, it's still sugar molecules and it's still water molecules, okay? And actually that's why it's still just a mixture, because you still have your little entities, okay? They mix homogeneously as long as you don't put in too much sugar, okay? But they're still little sugar molecules, okay? That's an example of a physical change. But not always when something appears to dissolve is it a physical change. That's why it says sometimes. So I think I have an example coming up of that. Okay, so we're going to take one more look at this idea of something in its three different phases. So this is water, solid, water, liquid, and water, gas. So when you guys were gas particles in here, you guys were just running around. No little yellow bonds, okay? Okay, and when you were solid, lots of bonds, and all you could do was wiggle. So this actually is a figure from an earlier, part one, where we talked about something in its solid state will have a high degree of intermolecular bonds, the lowest amount of kinetic energy, and basically the size and the volume and the shape that solid is, it's stuck with. Okay? If we compare that to a gas, it has no intermolecular bonds, a lot of kinetic energy, and gases are very, I'll go ahead and give you, gas will take as much room as you'll give it. Okay, take on any shape. Mm-hmm. It does. Gases expand everywhere. So again, kind of a repeat sort of thing. Those yellow, and I didn't bring them, but when you guys kind of connected with a high connection when you were solid particles, those were these intermolecular bonds or interionic bonds. Okay, so solid is really connected. Gas is not connected at all, if it's behaving ideally. So again, just kind of talking about now phase changes. So they're listed on purpose, solid, liquid, gas. So we can go from left to right, from solid to a liquid or liquid to a gas, if we add energy and break bonds. Okay, so that first one is we add energy. you know, it's an add energy, and I'm going to go ahead and say add external energy. So some outside source to break those bonds. Maybe not as intuitive. It's not as intuitive to me. But when stuff goes from, as it's up here, when stuff goes from right back to left again, that happens too. Let's see, what's a good example? Well, I teach weather this semester, so I usually will kind of point to a cloud. And if you can see the milky white of a cloud, the reason you can see it is because that water is now not water vapor in the air, because we know there's an amount of humidity in this room, but now that water is actually liquid, and that's actually why you can see it, because it has some cool things with light. So this idea of, and there's a word for it, we're going to call that condensation, this idea of condensation. Something going, doesn't have to be water, but it can be. Something going from a gas to a liquid is condensation. Actually, energy is released. Energy for E for energy is released. And that actually is a player in, if you're one of these fans of severe weather, that's a player for those tall clouds, okay? The reason they can get so crazy tall is because when the clouds form, they basically bring with them a certain amount of heat that makes it, the whole thing want to rise, okay? So it kind of feeds on itself. So when substances like water go from a vapor or a gas to a liquid, energy is released. When substances like, again, water, when you put your ice tray in your freezer, okay, and to go from a liquid to a solid, energy is released, okay? And let me go back 1 minute. So down here, let me go ahead and highlight this. Actually, for tomorrow's lab, you will need goggles. Okay, for tomorrow's lab. And tomorrow's lab, there are no right or wrong answers. You do great in tomorrow's lab. Just come, all right? And you guys are going to want to kind of apply some of the terms that we've been talking about in lecture in tomorrow's lab. You're just going to kind of take off. We won't take off. We'll kind of go through a series of small experiments. If you have your lab book, you can kind of see it's called Scientific Method and Observations for tomorrow's lab. So just kind of you might want to have this handy. So in tomorrow's lab, you might run into some things that require energy, and you might run into some things that release energy, or exothermic. Okay, so in this case, right now in this class, we're talking about intermolecular bonds. When we're talking about it takes energy to break those intermolecular bonds, and energy is released when those intermolecular bonds are formed. Those little yellow things. So in case make sure we're all on the same page, okay, I'll put these four up. You're probably real familiar with the first three. You may not be, no, where it is? I guess there. I'll put these up. Actually, they're in pairs now that I look at them, aren't they? These go together, and these go together. So we need to add energy to melt stuff, and when stuff freezes, energy is released. I'm going to change my color of my pen. And we need to add energy to evaporate stuff, and when stuff condenses, energy is released. I mean, it makes sense, right? So here's a little animation. Here's one for you. So, boy, gas today, like I get BP points or whatever, and it was like $1.52. No joke. That's amazing. I don't know if y'all are anybody in here old enough to know, like when gas was like 76 cents a gallon. Really, when growing up, 76 cents a gallon.
I don't remember it that cheap, but I remember when it was like down to under $1, like almost right under $1, and that was in the city.
Yeah, and it's
in
amazing.
Chicago.
Yeah.
It's always double what it is.
That's still low.
Yeah.
So I'm hopeful. But my point was going to be when you gas up your car, do you ever smell the gas? So, smell, you could not you'd have a hard time being a chemist working in a laboratory if your nose didn't work, because honestly, you count on smell as being a property of matter that can kind of urge you to leave the area or make sure your fume hoods are working. So odor, smell is kind of important. But my point was going to be the fact that you smell your gas that you're putting into your vehicle means that those gas molecules, that molecules of gas has made it. Molecules of gas. It's funny, we call it gas, but gas is also physical phase. So gas in its liquid state actually has gasified and made it to your nose. So that's what this actually is going to kind of talk about that. There's this kind of an equilibrium depending upon how volatile, that's actually property, how volatile a liquid is. And this is kind of talking about kind of a volatile liquid. Although, haven't you ever left a cup of water, especially if your house is kind of dry, if you leave a cup of water for a week or so, what happens to that water?
It evaporates.
Yeah, it evaporates. It's kind of a natural process. Those bonds are broken. So let's play this little video to kind of get you thinking about what's happening when something goes from a liquid to a gas, or liquid to a gas and vapor are the same thing. So again, this is showing liquid water and heating it. That's your external heat. And some of those intermolecular bonds are broken, so these gas particles, they're free. Okay. Na-na-na-na-boo-boo. So this one you may or may not be real familiar with, this phase change that basically skips the liquid state. So on either side of the liquid state we have solid and gas. So it's possible for something to go straight from a solid to a gas. And it's possible for something to go straight from a gas to a solid. Good case in point is if you've ever, don't play around with it, but dry ice. Dry ice is basically carbon dioxide molecules of CO2 that have been forced to stick together in their solid state under cold temperatures and high pressures usually. So CO2, cold, right? Okay. So carbon dioxide, dry ice, when you put it in water, or don't put it in water, you just kind of put it on the table, what's it do?
Becomes smoky.
It becomes smoky, yep, and it just goes from its solid to its gaseous state. This is one thing I looked up, and I gotta believe this is true. So that smokiness that we think is so cool from dry ice, okay, that's not really CO2, okay? That actually, it's indirectly CO2. What's happening is the CO2, in order to break those bonds, okay, it's robbing energy from the air. That's why it's so darn cold. Oh, bird, that stuff is cold. Dry ice is really cold, okay? Dry ice is really cold because it's robbing thermal energy from the air, from your hand, whatever holding it. It's robbing it so it can break those intermolecular bonds and go straight to a gas. That's why it's so cold. So the thing about the milky white stuff is basically where it's so cold, that is where it's kind of like a cloud phenomenon, where clouds are formed because water has gone into its liquid state. Basically, that's little liquid water. And the reason it kind of goes like this is because CO2 is a fair bit denser than the nitrogen and oxygen in the same. So anyway, so we call that sublimation. When something skips its liquid state, solid to gas, sublimation. Okay. There's another good example, or a good example of the opposite one. When something goes from a gas straight to a solid, skipping the liquid state, and that is frost. Okay. Have you ever thought about the thing, like if my finger is a blade of grass, as it gets cold at night, basically water vapor, water gas, goes directly, especially if it's cold enough, goes directly from being a vapor to being a solid. Okay, we also call that sublimation. Actually, this from a gas to a solid, it can be called sublimation. I prefer deposition. Same thing. So this is we're gonna do an or show you a little video here, and this is the element iodine. Okay, iodine is what's the symbol for iodine? I. It's just a simple I. Very good. And the other thing about iodine, I told you guys my little trick about the Hoffer nickel elements, didn't I? Okay. Those are the special 7 elements that come in pairs. They're diatomic elements. So actually it's really I2. So it runs around. Well, it's just I, but it runs around as a diatomic element. So let's see what this looks like. Okay. So energy can either be required, okay, or energy can be released. So the phase changes that are required are where bonds are broken. That would be the melting, the evaporation or vaporization, and the sublimation when something goes from a solid to a gas. So the things where energy is released are these. Okay, so energy is released when something liquid goes to a solid. We call that freezing. Energy is released when something goes from a gas to a liquid. Condensation. Energy is released when something goes from a gas to a solid. We good with that? Okay. So it takes energy to break bonds, and when bonds are formed, energy is released. Sounds like it should be a song. So again, we'll be kind of talking about this in tomorrow's lab when you're kind of on your own doing little things. Sort of on your own. On your own, but together.
Yeah, you don't want us blowing nothing up yet.
Which reminds me, a few students that couldn't make it for that first Thursday lab, y'all really need to, can you be here a little bit early? Lab starts at 9, so if you could even come like 10 minutes early. Because I really need to, if you don't come 10 minutes early, then I'm going to have to wait, because I need to show you the safety features of lab. Okay, so we talked about chemical properties, and a chemical property can be measured, but you have to destroy the sample. Remember I said that? Basically, a chemical property would be measured using a destructive test, because new substances are formed. So same thing when we talk about a chunk of matter that's undergone a chemical change. What's that mean? New substances are formed, right? Chemical change. You don't have the old stuff anymore. Okay. So if I kind of, do you guys have this one again? Okay. So remember, I kind of said that if I pick on these 2 elements, we can take the individual atoms and build them up to form a compound using some sort of chemical reaction, CHM122, okay? So I kind of went from left to right. We can do that. We can take some sort of chemical reaction and break a compound down into its elements. Okay? So going back and forth between an element or a compound to break it down to its elements, these would definitely be a chemical change, CHM change. Does that make sense? But the thing about over here is actually this looks pretty. You think you could separate those 2? Pretty much. Yeah, you could skim the oil off or whatever. Take a little turkey baster and suck off the oil, and you could physically. My point here is that we can always physically separate. Ooh, spell separate. Okay, a mixture back into its components. Sometimes it's harder than others. Sometimes, like, I have no idea, but some of them are easier than others. So that would mean if we can physically separate, the act of separation actually then, would that be a physical change or a chemical change? The act of separation would be a physical change, exactly. Dang. Boy. Okay. My spelling sometimes. So we talked about physical changes. Okay. No new substances are formed. Now, here are some examples of chemical changes that I don't necessarily, I'm not anxious to do in the lab as demonstrations. So I've mentioned it before. Chlorine, Cl. That's one of Hofbräunickel's 7 elements. Okay, so that's why you see it as with a little subscript 2. Phosphorus is one of those that actually is kind of like the diatomic elements, but it is most stable when it has a buddy of 4 running around. So that's why it's P4. I might hold these for later. I kind of want to get to the assignment slide. All right. So that looks like a galvanized nail to me, which is not supposed to rust, right? Yeah. But anyway, you guys told me that when iron rusts, that's an example of a chemical property of iron. And that's all this is showing you. So the gray would be individual iron atoms minding their own business. And here the rust would be, you can kind of see that oxygen has inserted itself. So iron oxide. This one, and I have actually a couple slides here for this Bic lighter, this butane lighter. So the formula for butane is C4H11, okay? So here's your cute little liquid butane in here. Now the thing about butane is that left on its own, it would be a gas in this room. But basically, is that right? But this is under pressure. Under pressure. So when you open this, basically, because this is pressurized, its contents squirt out. And what does butane want to be? That C4H11 want to be? It wants to be a gas. So up there, those are gaseous butane particles. Here, these are liquid butane particles. Isn't that fun? So, of course, then, when you hit the striker, it goes ahead and it ignites. It basically begins the combustion process for that butane that's coming out in its gaseous state. Okay, so it takes, up there, combustion is basically, here it's taking the butane, C4H, what I've been calling it 11, okay, and it mixes with the oxygen from the air, and it makes CO2. Do you see the CO2? And cute little H2O molecules. Okay, so new substances are formed. That's the combustion. Okay. Now, doesn't this look like fun? I mean, you know, you're like, whoa, but yeah, you just kind of stick the pieces of glassware together. And all it is we have a mixture here, and of course, there's the Bunsen burner, so it starts there. We have a mixture of 2 liquids that they're not like oil and water, they're miscible. 2 liquids that are like formed a mixture, a homogeneous mixture. So, one of the things you know about liquids probably is they boil at different temperatures. You know, gasoline would boil at a very low temperature compared to water, okay? So you could put gasoline in water here, and basically at a low temperature, your gas particles, your gas, okay, would come up. This is called a distillation. It would come up here, your gas particles, and this right here is cooled with water. It's got like a jacket. It's hollow on the inside, so your gas or whatever can fall down. But on the outside, it has water running. Okay. And so then what we count on is that gas that you heated it up to its boiling point. When it finally gets in this condenser tube, it's going to go ahead and slow down and re-liquefy. Slow down, gas particles. Okay. And then it's going to drip into here. Isn't that adorable? Okay. Actually, you probably heard this technique can be used to kind of purify water too. If you just wanted the particulates to stay behind, the residue would stay over here, and you'd have your water come over. But I think it's much more interesting to have 2 liquids like that. And they'll come over in fractions. So basically, if it was gas and water that you were trying to separate, you could go at kind of a very low temperature at first to get all your gas over, and you could be testing this. Make sure you had no water. You might have some water. And then at a certain point, it would stop coming over, and you'd have to jack up the temperature to get if you have 3 components, you can kind of do it that. But separating it based upon boiling point temperatures. Okay, this one's kind of straightforward. Basically, in here, you had a mixture, and in this case, the mixture was heterogeneous, so you had sludge at the bottom. And basically, you're trying to isolate that sludge from your liquid. That's what filtration would do well for. But whether it's distillation or filtration, can you see where these are just physical changes in that overall chunk of matter you were trying to separate? Okay, no new substances are found. Okay, so I'm going to go physical, chemical. Some of these are harder than others. So let's say my thing, by the way, is, I'm just going to put this on the board. The mantra I ask myself, because by the way, you will on your test be faced with questions like these, okay? But basically, physical, whether it's a property or a change, no new substances. And the other thing, if it's a physical property or change, it can be undone. Okay? And chemical, you do get new substances, and you can't get your old stuff back again. So I usually say can not be undone. I'll go ahead and qualify that without another chemical reaction. I better qualify that. They can be undone, but it's hard to undo them. So, with that in mind, how many people think that if you accidentally bleach a piece of clothing, that how many people think that that's a physical change? How many people think that's a chemical change? Me too. It's a tough one, I think. Okay. So this is talking about water going from a gas to a liquid. Now remember, we talked about this. How many people think that when water goes from a gas to a liquid, how many people think that's a physical change? Me too. Very good. The next one, the fact that plants are great at converting CO2 to ultimately making sugars. Okay, how many people think that's a physical change? How many people think that's a chemical change? Very good. You got it. Okay, next one. What about, see, butter usually is a solid, okay, and this is actually just talking about it going to a liquid. So basically when water goes from a solid to a liquid, how many people think that's a physical change? Me too. See, you're great. You're great. Okay, any questions over? So this will be due, I'll take you to the website. Was it 41 through 44? Mm-hmm. Okay, good. They're not too bad. I just kind of put these up to encourage you. Okay, let me make it smaller, maybe. Any questions? These will be due on Friday. Fabulous Friday. Okay, that's all I had. Remember your calculators on Friday, okay? And if you have any questions about your calculators, let me know.
Yes, because I have this one, and I purchased it for my